In this video, we're going to look at a few more examples of the basic comparison test. Determine whether the following series converges or diverges. Question A, summation n equals 1 to infinity log n divided by n squared. Question B, summation n equals 1 to infinity 3 to the power of n plus n divided by 5 to the n. Question C, summation n equals 1 to infinity 2 plus negative 1 to the n divided by root n. Let's look at part A first. We have summation n equals 1 to infinity log n divided by n squared. We know that log n is less than root n for n larger or equal to 1. How do we know that? This is a property of log functions that log x is always going to be less than kx to the p. It's always going to be dominated by these power functions of the form k times x to the p. Provided the exponent p is positive, the constant k is also positive, and x is sufficiently large. This will form the basis of our comparison. Alright, so we have summation log n divided by n squared, and we have log n divided by n squared. Every term of our given series is less than every term of a comparison series, root n divided by n squared. Let's simplify this. This is n to the power of 1/2 divided by n squared. Subtract off the exponents, we get 1 divided by n to the power of 1.5. We also know that summation n equals 1 to infinity summation n equals 1 to infinity 1 divided by n to the power of 1.5 is a convergent p-series. Convergent p-series. Why is it convergent? Why is it convergent? Because p is equal to 1.5 greater than 1. The value of p is larger than 1. So we can say the given series summation n equals 1 to infinity log n divided by n squared is convergent by the basic comparison test. By the basic comparison test. So this is the key. Every term of our given series log n divided by n squared is less than every term of a comparison series, which is a convergent p-series, because p is equal to 1.5 greater than 1. So by the basic comparison test, the given series summation n equals 1 to infinity log n divided by n squared is a convergent series. So let's summarize. Summation n equals 1 to infinity log n divided by n squared is less than summation n equals 1 to infinity root n divided by n squared, which is equal to summation n equals 1 to infinity 1 divided by n to the 1.5. And what we have here on the right hand side is a convergent p-series. Convergent p-series. Why is it convergent? Because p is equal to 1.5 greater than 1. So what we have is our given series, every term of our given series is less than every term of the comparison series, which is a convergent p-series. So by the basic comparison test, our given series summation n equals 1 to infinity log n divided by n squared also converges. Alright, let's look at part B. For part B, we have summation n equals 1 to infinity 3 to the power of n plus n divided by 5 to the n. Now we know that 3 to the n, the exponential function, will always be greater than the linear function for n larger or equal to 1. So that is for sure. And now looking at the dominant term in the numerator, which is 3 to the n, and a dominant term in the denominator, well, there's only one term in the denominator, so that's the dominant term, 5 to the n. It's logical that the series that we're given, the given series, summation n equals 1 to infinity, 3 to the n plus n divided by 5 to the n, behaves like the geometric series, summation n equals 1 to infinity, 3 to the n divided by 5 to the n, which is a convergent geometric series, summation n equals 1 to infinity, 3 divided by 5 to the power of n. The common ratio, absolute value of r, is equal to 3 over 5, is less than 1, So intuitively, we know that the given series must converge because it behaves like a convergent geometric series. But we have to formally verify our intuition by applying the basic comparison test. All right, so what we have is a summation n equals 1 to infinity, 3 to the n plus n divided by 5 to the n. We know that n is less than 3 to the n for all n larger or equal to 1. So we have 3 to the n plus n is going to be less than 3 to the n plus 3 to the n, because n is less than 3 to the n. And this is equal to 2 times 3 to the n. Now, divide both sides by 5 to the n so we can form the terms of the given series. Divide both sides by 5 to the n, divide by 5 to the n. And we now have this inequality. We have 3 to the n plus n divided by 5 to the n, which is the general term of our given series, is less than 2 times 3 divided by 5 to the n. If you notice, this is a convergent geometric series with common ratio 3 over 5, which is less than 1. So every term of our given series is less than every term of a convergent geometric series. Let's write that down. So summation n equals 1 to infinity, 2 times 3 divided by 5 to the power of n is a convergent geometric series with r, absolute value of r, is equal to 3 over 5, which is less than 1. That means the given series, summation n equals 1 to infinity, 3 to the n plus n divided by 5 to the n, converges by the basic comparison test. Converges by the basic comparison test. Let's just abbreviate that, basic comparison test. All right, let's summarize that. So what we have is the given series is summation 3 to the n plus n divided by 5 to the n. N goes from 1 to infinity. Every term of our given series is less than every term of a corresponding comparison series, which in this case is a convergent geometric series. So 2 times 3 divided by 5 to the n equals 1 to infinity. And on the right-hand side, we have a convergent geometric series. Why is it convergent? Because the common ratio, r, is equal to 3 over 5. Its absolute value is 3 over 5, less than 1. And every term of our series is less than every term of a convergent geometric series. So by the basic comparison test, the given series, 3 to the n plus n divided by 5 to the n, also converges. All right, let's look at the last question, part C. So here we have summation n equals 1 to infinity, 2 plus negative 1 to the n divided by root n. Now, we know that negative 1 to the power of n is equal to 1 for n even. And negative 1 to the n is equal to minus 1 for n odd. So we can write the numerator 2 plus negative 1 to the n. Let's find an upper bound for it. That's going to be 2 plus 1, which is 3. A lower bound would be 2 minus 1, which is 1. All right, now let's divide everything by root n. Divide by root n. Divide by root n. So the given terms of our series 2 plus negative 1 to the n divided by root n is larger than 1 over root n. But you will notice that 1 over root n is a general term of a divergent p-series, because summation 1 over root n equals 1 to infinity, is a divergent p-series. Why is it divergent? Because the exponent p is equal to 1/2 is less than 1. Because we can write this as summation n equals 1 to infinity, 1 divided by n to the 1/2. 1/2 is the value of p. P equals 1/2, less than 1, so it diverges. So that means the given series that we have, summation n equals 1 to infinity, 2 plus negative 1 to the n, divided by root n, diverges diverges by the basic comparison test. Again, I'll abbreviate basic comparison test. And so let's summarize. We have summation n equals 1 to infinity. That was our given series, 2 plus -1 to the n, divided by root n. This is larger than a given series, it's larger than a comparison series, which in this case is a divergent p series, 1 divided by root n, which is summation n equals 1 to infinity, 1 divided by n to the 1/2. And on the right-hand side, we have a divergent p series. Divergent p series. Why is it divergent? Because p is equal to 1/2. Let's write that better, 1/2, less than 1. So every term of our given series, 2 plus -1 to the n divided by root n, is larger than every term of a comparison series, which is a divergent p series. For this reason, the given series that we have diverges by the basic comparison test. All right, thanks.